because it was very important for the practical applications in the field. Because if we are going to use this material for stormwater applications, when we can use the natural hydrological cycle and prolong the lifespan of the system. So it's very, very important characteristic. The material is also cheap and locally available, and there was evidence in the international literature that other steel slag types were used for wastewater. So everything that I showed prior to this slide was done only on laboratory solutions, not on real wastewater. So in 2004, I became professor at the University of Vermont, and also because they were looking for solutions for phosphorus removal, because as I said already, it's a very important lake. Lake Champlain is a very important lake in Vermont, even though it's a very small state. So we have Quebec here, we have New York State, and we have Vermont, and it's heavily polluted with phosphorus. So in January 2011, actually, the Federal Environmental Protection Agency took over from the state cleanup of the lake. Because for years the funding was given to projects, based on laboratory research, not on practical solutions, and the water quality of the lake just continued to deteriorate. So now we have Environmental Protection Agency trying to solve the problem, mainly by building mathematical modeling. No funding is still given for any kind of practical solutions. However, in 2003, the Constructed Wetland Research Center was built. This was prior to my arrival to University of Vermont at the cost of $1.6 million US. And when I came for my job interview, I told them already then that this system will never remove phosphorus, because I already had experience with constructed wetlands. So the system was basically designed to treat all this wastewater from the barnyard and milk parlor. We have sedimentation tank, and then with pipes we bring mixed water from barnyard and the milk parlor in the flume here, and the water is distributed to 4 wetlands like that. We have the outlet point here, and then the water flows to Potter's Brook, which is tributary of Lake Champlain. And of course, design objectives were to remove everything. So this is just a look of the system. I will not go into details of all of this, but for 5 years I directed research. I was director of this Constructed Wetland Research Center as well as professor. So I directed numerous experiments on the performance of these constructed wetland systems for contaminant reduction, nitrogen transformation, hydraulic behavior, the effects of temperature. There were many, many papers published on the performance of this system. And these are some of my students working on the site, just to make it more interesting. In parallel with all that research on constructed wetlands, I raised additional $700,000 in funding, and we built this small, very small phosphorus research facility. But we managed in this small research facility, so we have constructed wetlands on both sides and there. In this small facility, we managed to place 12 different columns. This was my first master's student and the first student who worked with looking at the steel slag filters for dairy effluent treatment, real dairy effluent treatment. And this site enabled us also to build really interesting, in one side we were collecting effluent from constructed wetlands. So we simulated what would happen if we build a filter after constructed wetland. In the first one on this side, we actually took effluent without any pre-treatment, and we wanted to run the systems in very, very difficult operating conditions so that we could actually clog them and decrease their lifespan, and to try to understand removal processes. We also had a number of small-scale experiments where we looked at removal mechanisms, at different loading, different materials. This little hut here provided, it's hard to believe, but I'm very proud of this, the fact that it provided numerous possibilities for research. I have 5 master theses of this small hut that the total invested in building this research facility was $1,000 as opposed to 1.6 million, just to give you an idea. As it goes with our government, they said, okay, this first research here, the columns were housed in the hut. We only put 20-degree temperature Celsius during January and February. So we were not heating the facility all the time. But people from the government who announced funding programs said, well, this was actually heated facility, so we want to see what will happen in harsh winter conditions if the systems are outside. So we built more pilot-scale systems outside our phosphorus research facility, but at the same site, and started investigations on what can be done with the filters with some complicated piping, doing vertical, horizontal, upflow, downflow. If you have any interest on what we did in this research, you can email me. I will send you papers and speak about that, but I will not go into details. I just wanted to show that there was enormous amount of research and that we did investigate all possible conditions, which enabled us later to make many different designs. So you can see the list of various conditions, various sizes, retention times, every possible condition was investigated. Following 2006, between 2006 and 2008, I managed to get a small funding from the Environmental Protection Agency, who was interested in looking at my filters for non-point pollution phosphorus removal projects in Upper Vermont. So we designed a few small-scale systems to treat agricultural runoff treatment, industrial park runoff treatment, agricultural tile drainage, and urban stormwater treatment over, and we monitored these systems over a year and a half. And this is just to give you the idea. So one of them was located for urban runoff treatment on the parking lot that was going into the channel. Our tile drain was located there, and it was going into very sensitive and extremely polluted bay, St. Albans Bay in Vermont. And in the industrial park, we had algae accumulation, so the systems were placed in these areas. Together, the research that I showed that we performed at Constructive Wetland Research Center at University of Vermont and these projects outside Vermont, we achieved really excellent efficiencies, 95% of phosphorus from point pollution sources, 90% of suspended solids, 80% of non-point pollution sources, 75% of suspended solids, excellent E. coli removal, and as well as other minerals, mainly copper, sulfur, and zinc. So the systems are also efficient and beneficial for the environment because we do not have any chemical addition. So if we were going to design phosphoric system for municipal wastewater treatment plants, we can avoid addition of salts of iron or aluminium. Therefore, we will minimize sludge accumulation and decrease the cost of operating wastewater treatment facility. Because the material is so efficient, it has smaller land area requirements compared to constructed wetlands or some other technologies like circulating filters or other technologies. We have minimal or basically no energy requirements because in most cases we use gravity. And again, because of the efficiency of the material, we have longer lifespan than other filter materials. And we also performed research that Dr. Gustafsson and Dr. Renman and Lena started on steel slag material reuse as a soil amendment or commodity fertilizer. We just work with different type of steel slag material and different plants. They work with barley, we work with local red clover, local grasses. And we were just looking at the potential for reuse of this phosphorus for plant growth. For example, it would be very useful in acid mine drainage for the reclamation, because there the soil usually has very low pH. So if you put this type of reused material from the filters, we can help vegetation establishment. And the systems are also very versatile. We can design for different, depending on the use, they will be different size and for different applications. So it's never boring. We are always challenged to find some new design to apply for a specific situation. Encouraged by the University of Vermont in 2007, I established a small business, Phosphorus. It's mainly because I live in Quebec, so it has to read both in English and French, phosphorus reduction. And that's why it has this incomprehensible name. A lot of it are difficult to pronounce. And it's really the only business that specializes in sustainable, innovative technologies for water pollution control. We do various pollutants removal, but our major focus is phosphorus. I remain faithful to phosphorus. And we currently have 2 pending patents. I would say forever pending, because it takes about 6 years in the United States to get a patent. How long it takes in Sweden? Longer or shorter?
6 years.
Okay. Depends how much we pay. Okay. Anyway, so we have 2 different ones. One is for we have one for point pollution source, phosphorus removal from point pollution sources, and we have one for stormwater outlets, so for non-point pollution sources. And I just wanted to summarize again here that prior to Phosphorus, I just want to make a little summary that I raised $1.5 million in federal funding and established over 40 demonstration projects in 5 different states. These were like my research projects. Numerous peer-reviewed scientific papers. I trained dozens of graduate students from across the United States and Canada, as well as internationally in Taiwan and Brazil. And over the past 5 years, I gave over 50 presentations across the globe promoting my technology and the need for phosphorus removal. So despite all of that, and significant amount of research from other parts of the world, like here in Sweden, I always wonder why we only have very few full-scale systems implemented in the United States, and what needs or what can be done to change this situation. And here we come to the approvals. I hope I will have a chance to learn maybe after today's conference, like how the system works in Sweden, but this is how it works in the United States. We have U.S. Federal Environmental Technologies Verification Program, and I think that every country in the world has developed their own ATV, Environmental Technology Verification Program. These approvals are extremely costly. In the United States, it costs $120,000 per application to get your certificate. We have developed in Phosphorus 6 different classes of technologies. So if you translate this, if I'm going to ask for a permit for agriculture runoff, I need $120,000. I need for municipal treatment like $120,000. For residential, so it's enormous amount of money for a small business, for anybody, for any innovator, any scientist. It's basically impossible to get. But I'm a very persistent person, so I went into a long path of individual state applications. And in this case, we do not need to provide any financial investment at the time of application, but it takes about 36 months to our government to decide whether your system can be considered for some kind of general use or not. And normally what happens is that about 8 to 14 months later, the government comes back to you and they say, well, you can go and implement the system, but you have to perform additional water quality monitoring, which costs about $50,000 and also 18 months in your time. of any kind of application, because this is how long it will take for this water quality